Hello there, my name is Malika Detunji. I'm a graduate student at the Department of Physics, WIU. I worked with Pradeep Bhattarai under the supervision of Professor Kishore Kapali to simulate quantum error correcting codes on IBM's quantum computers. I will be taking you through the outline of this presentation. As an introduction, I will explain some basic concepts that are relevant to quantum information and quantum error correction. And then I will explain the stages involved in quantum error correction. Specific to this project, I will be showing you a 3-qubit quantum error correcting code and explaining the different parts involved. The results obtained from this research will be presented after that, and the conclusions that were made from this research will also be discussed. Future trajectory of this research work will be presented. Classically, the basic unit of information is a bit. That is, in classical computers, information are stored in the smallest units by zeros and ones. For example, a 12 is known to a computer as a 1100. Also, bits can never occur simultaneously as zeros and ones. They can either be 0 or 1. Physical examples of bits are transistors, capacitors, voltage pulses, and circuits. I would also like to talk about quantum computers. In quantum computers, the basic unit of information is the quantum bit. The quantum bit, also known as the qubit, can exist in a coherent superposition of a state 0 and a state 1. What this means is that a qubit can simultaneously be a 0 and 1 with different probabilities or the same. This is a pictorial representation of the different states that a qubit can exist in. Physical examples of qubit states are atomic spin state, electronic state of ions, the polarization of photons, and the charged state of superconducting circuits. It is important to note that each of these systems are two-level systems. For example, the spin state of an atom are spin up and spin down. A spin up could represent the state 0 of a qubit, while a spin down could represent the state 1 of a qubit. Also, because each of these physical systems are at atomic scale, they are easily disturbed by their environment. Every interaction with their environment could potentially corrupt their state and cause a loss of information. When something called decoherence occurs, decoherence is actually a loss of their superposition. When that occurs, it becomes hard to do quantum computation or quantum information because qubits are special due to their superposition. However, the interaction with the environment is unavoidable. So we need to find a way to reverse the effect of these interactions. This is where quantum error correction comes in. What are the types of errors that could occur due to this interaction by the environment? There are several types, but two main types are bit flip and phase flip. Now, a bit flip is an error that changes a state 0 to a state 1 and vice versa. However, while a phase flip changes a state 0, it leaves a state 0 unchanged, but changes a state 1 to a negative 1. The stages involved in quantum error correction are mainly 3. The first stage is the encoding stage. It involves taking a specific number of physical qubits, performing operations on them, and using those qubits to represent a single logical qubit. Now, a logical qubit is basically a qubit that is error-free. Detection stage involves using extra qubits to check the qubits that were used for encoding. Now, what do we check? We check for the parity. The parity helps us to find the location of the error in those encoded qubits. Now, the correction stage just involves the use of some quantum mechanical operations to correct the errors based on the results of detection. Here is a typical example of a quantum error correcting circuit. To be specific, this is a 3-qubit quantum error correcting circuit. Here we have the encoding part where we take 3-qubit Q0, Q1, Q2 and encode a single logical qubit. If we introduce an error, an X error, which is a bit flip error here, that is, the qubit Q0 would be flipped. We would then need a detection stage, which checks for the location of the error. And finally, based on the information we obtain from the detection, we perform error correction. Each of these symbols here are gates, and they have mathematical representation. For example, here we have a C0, which is this. And we have the H here is the Hadamard gate. The Hadamard gate is what is responsible for creating the superposition of a state. I will now explain how this 3-qubit error correcting code works. First of all, in the encoding section, we take an initial state, state 0, and using the operations, the Hadamard operators and the C0 operators, we create a 3-qubit encoded superposition state, alpha 000 plus beta 111. By introducing an error on the first qubit Q0, we then measure the state of the ancillars A0, A1. By measuring the state of the ancillar A0, A1, we obtain A0 and A1 as 1, 1. That guides us to perform other operations that will correct the error that was placed on the qubit Q0. Depending on the states of the ancillar A0 and A1, we would write codes. We would build quantum gates to correct the error. Say, for instance, if we measure the ancillars A0 and A1, and we have the results of our measurement are 0 and 1, that tells us that the error is actually on the third qubit, Q2, and then we can correct the error. But the purpose of this particular circuit that we can see is to do the correction automatically. Here, the detection is done automatically by the circuit, and depending on what the results of the ancillars are, the error correction is done automatically. Here we measure the 3 qubits that were encoded initially to check if the error has been successfully corrected. Now, after writing a code using Python programming language on IBM's cloud platform called Qiskit, the Qiskit is a quantum computation platform that is used to write circuits for correcting codes and several other purposes. Now, after writing the code and simulating it on the cloud platform, we obtained this result. This result means that there is 50% probability of obtaining a 000 state, as well as another 50% probability of obtaining a 111 state. This means that our input state 000111 is what we obtained after correction here. Therefore, we can conclude that our error was successfully corrected. However, when we implemented the same code on actual quantum computing hardware of IBM, we found that the error fails. It fails to correct we found that the error correcting code fails. This is obvious from the intermediate state that are produced. Not only do we have a probability of having a state 000 and a state 111, we also have probabilities of having other intermediate states which were not encoded in the circuit initially. So therefore, the error correcting code fails. We can conclude from this work that error correction can be automated using error sync. And we can also conclude that when the error rate is low enough, the 3-qubit quantum correcting code can successfully correct a single bit flip error. This is seen from the simulation results over here. However, when the error is high enough, the 3-qubit quantum error correcting code will fail, as seen when we implemented the code in actual hardware. So we can say that currently the hardware that we have high noise rates, and that overwhelms our 3-qubit codes and causes them to fail. This is obvious from the results that we obtained here. Based on what we have observed, we would like to implement other available quantum error correcting protocols. To be specific, the 5-qubit code, the 7-qubit code, the 7-qubit code. We would like to investigate how they would perform in actual hardware. This is the direction of the project going forward. Thank you very much for listening. I will appreciate any questions you have. Please put them in the comment section, and I will respond to them as soon as possible. Thank you.